Hello dear colleagues. In the previous lesson we spoke at length about algorithms and models, about complex neural networks and elegant mathematical approaches. But any model, even the most sophisticated, is just a high-tech engine. And every engine to run needs fuel. In the world of artificial intelligence, that fuel is data. Today we will take a deep dive into this topic. We will explore what data is in the context of artificial intelligence, what forms it can take, and why proper, thoughtful, and responsible handling of it is, without exaggeration, the foundation of success and safety in any AI project. In this video we have also prepared a mini quiz to test your knowledge. Don't forget to subscribe to our channel so you don't miss the next lessons. So, let's start from the very beginning. What exactly is data? Formally speaking, data are the set of discrete, objective facts about an event or object, presented in a formalized form suitable for storage, transmission, and processing. In the context of artificial intelligence, data are the very empirical foundation on which models learn to identify patterns, make predictions, and ultimately make decisions. Put simply, data are any recorded information about the world around us. It can be anything: the text of this lesson or customer reviews on a website, numbers in financial transactions or air temperature readings, photographs you take on your phone or X-ray scans in a hospital, recordings of human speech, music, or even the sound of an engine running. For artificial intelligence, all of this is just raw material. And here we arrive at the key thesis: AI models do not work with ideas, they do not understand context, they work exclusively with numerical representations of data. The specialist's task is to turn that informational chaos into a structured set of numbers that a machine can work with. To better understand what we are dealing with, let's classify the full variety of data along two key axes. The first axis is structure. Structured data are highly organized and fit perfectly into the familiar rows and columns of a table. Imagine a CRM database with fields like name, phone, purchase date, or financial spreadsheets in Excel. For most classical machine learning models, such as regression or decision trees, this is the simplest and most straightforward type of data. Unstructured data, by contrast, is what we might call creative chaos. Information with no predetermined structure or format: an email's text, a YouTube video, an audio recording of a conversation, social media posts, images. It's important to understand that working with these kinds of data, which make up as much as 90% of all information in the world, is what led to the deep learning revolution we see today. Finally, between these two poles lies semi-structured data. They don't fit into strict tables but contain tags or markers that help separate semantic elements. Good examples include JSON files used throughout web development, or emails where fields like to, from, and subject are structured, but the body of the message is unstructured text. So, we've seen that data can be as neat as a spreadsheet or as chaotic as freeform text. But there is a second, and perhaps even more important, axis of classification that directly determines what type of artificial intelligence we can build. This axis answers a simple but fundamental question: do we know the correct answer for our data in advance? Here data split into two large camps, unlabeled and labeled. Unlabeled data are a set of objects represented only by their features, with no associated, correct answers. These are data without hints. The model must, like a detective, find hidden patterns and structure on its own. Labeled data, on the other hand, are a set in which each object or observation has been paired with a target label that reflects the very correct answer or outcome the model must learn to predict. And I want to emphasize that the quality and volume of that labeling are the absolute foundation for building accurate, reliable models. And so that we all speak the same language, we need to remember two terms we've mentioned in passing, which form the basis of all machine learning. Feature, a measurable characteristic of our object, the input data for the model. It's the information on which decisions are based. For example, for a patient it might be age, cholesterol level, and blood pressure. For a house on the market, it could be square footage, number of rooms, and year built. Label, the correct answer, the target variable we want the model to predict. It's the model's output. For our patient the label might be heart attack, yes or no. For a house, it would be its final market price. Let's summarize this important thought. Unlabeled data consist of features only. Labeled data consist of features and labels. Understanding this distinction is absolutely critical, because the labeling process, that is, turning unlabeled data into labeled data by adding answers, is one of the most expensive, labor-intensive, and responsible stages of creating artificial intelligence. And it is precisely the quality of that labeling that will determine whether our future model becomes a reliable assistant or a dangerous, biased advisor. Now that we have our terminology, let's look at the journey of data. Data do not appear from nowhere and vanish into thin air. Understanding their life cycle is critically important for effective governance. This cycle consists of several key stages, which we will now briefly review. Collection, the stage at which we acquire data, via sensors, website logs, surveys, or by purchasing from third parties. Processing and cleaning, perhaps the most labor-intensive stage. Here we remove duplicates, fill in missing values, correct errors, and standardize formats. Always remember the rule, garbage in, garbage out. Feature engineering and labeling, the stage where raw data are transformed into meaningful features and, if necessary, enriched with the very correct answers or labels. Storage, deciding where and how to store data, in traditional databases, cloud warehouses, or so-called data lakes. Usage, the stage for which it was all intended, model training, analysis, report generation. Archiving and destruction, the stage where we decide what to do with data when they are no longer needed for active work. Now I want us to take a deep breath and dive into the most creative, most important, and perhaps most underestimated stage of this cycle, feature engineering. Formally, as we've seen, it's part of data processing, but in significance it is truly the heart of the preparation process. What is the essence of feature engineering? It's the process of using our domain knowledge, so-called domain expertise, to create new, more informative features from existing raw data. If data are crude oil, then feature engineering is the refinery that turns it into high-octane fuel for our models. A model can be as powerful as a Ferrari engine, but on poor quality fuel it won't go far. There is a fundamental law of machine learning I want you to remember: the quality of your model is determined not so much by algorithmic complexity as by the quality of its features. The best algorithm in the world with weak features will always lose to a simple algorithm with strong features. Let's look at three main techniques data practitioners use, with simple examples. Feature creation, a kind of alchemy. We take two or more existing features and create one new feature that carries far more meaning. A classic example is credit scoring. Imagine a model sees two raw features for a client: annual salary of $100,000 and annual loan payment of $55,000. To the model these are just two independent numbers. But we, with domain knowledge, know their ratio matters. We create a new feature, the debt-to-income ratio, by dividing payment by salary. This single feature, 0.55, instantly conveys financial risk better than the two original numbers separately. We've just turned data into knowledge. Feature transformation, here we don't create anything new but apply a mathematical function to an existing feature to make it more model-friendly. For example, company revenues may range from thousands to billions. If fed as is, the model reacts poorly to such spread. The solution is to take the logarithm. By logging, we compress the scale, and now all companies sit in a comparable numeric range so the model can evaluate them appropriately. Categorical encoding, models don't understand words. We must convert text categories into numbers correctly. Take the feature, city, with values, Tokyo, London, and Paris. It would be wrong to simply assign them the numbers 1, 2, and 3. This is because such numbering creates a false mathematical relationship. The model would assume an order, learning that Paris, with a value of 3, is somehow greater or more significant than London, with a value of 2. The correct approach is one-hot encoding. We turn one categorical feature into several binary features, asking questions like, is the user in Tokyo, is the user in London, or is the user in Paris? This way, the model sees no ranking, only distinct facts. We have successfully passed the information without introducing any distortion. As you can see, feature engineering is a powerful tool, but like any powerful tool, it carries risks. Misuse can produce biased, unfair models, and those are precisely the risks we'll discuss in the next part of our lesson. Now let's touch on one of the pillars of our course, data governance. Before we discuss complex policies and committees, we must lay the foundation. Every governance effort starts with measurement. In the world of data there are two fundamental measures that determine whether we can even trust our AI system: data quality and provenance. Data quality answers the question, are our data fit for use? We often hear, garbage in, garbage out. Data quality is a formal way to measure how clean our data are. It's not subjective, it's a set of concrete, measurable metrics. Let's review 6 key ones. Completeness. How few gaps do we have in our data? If half of the client records lack income information, any conclusions about their solvency will be extremely unreliable. Accuracy. How well does the data reflect the real world? If a database lists a client's age as 250 years, this is a clear accuracy error. Consistency. Are there any internal contradictions in the data? For example, a client cannot be registered in the system later than they made their last purchase. Timeliness. How current is our data? A model predicting demand based on last year's data will be useless. This is also where the critically important concept of data drift arises. This is the gradual divergence between the data the model was trained on and the real data currently coming in. The world changes, and if we don't track this drift, our model's accuracy will imperceptibly decline day by day. Uniqueness. Do we have any duplicates? If the same client is entered into the database 3 or 4 times, it will skew all the statistics. And finally, validity. Does the data conform to the established format? For example, the phone number field should contain only numbers, not text. From a governance perspective, the organization's task is not just to know about these metrics, but to implement a continuous process of monitoring them. Data quality is not a project with a beginning and an end, it's a continuous function, like keeping a house clean. The second foundation of governance is data provenance and lineage. They answer the questions, where did this data come from, and what happened to it? Imagine your AI model is a witness in court. Before listening to its testimony, any lawyer would ask 2 questions: where did you get this information, and have you discussed it with anyone else since you learned it? In the world of data, these questions are answered by provenance and lineage. Data provenance, in essence, answers the question, where did this data come from? It's a data birth certificate, documentation that clearly records its original source. For example, data was collected using Google Analytics or purchased from a vendor. This is needed to assess the initial level of trust in the data. Data lineage answers the more complex question, what path has this data taken, and what was done to it at each step? This is a complete, detailed map of the data's journey, an audit trail of all transformations. For example, data from CRM was merged with data from accounting, then the gaps were filled, and a model was trained on this data. This is necessary, firstly, for auditing and debugging if the model makes a mistake. Lineage allows you to trace the entire chain back and find the cause. Secondly, for reproducibility. And thirdly, which is critically important, for compliance with regulatory requirements. It is the only way to prove that you have met all requirements, for example, regarding the deletion of user data from the entire processing chain. Now that we understand what quality and provenance are, let's look at a risk map. In AI governance, data are not just a resource but the main object of control. Risks arise at every stage of their lifecycle. Collection, privacy risks, legal risks, and compliance failures, GDPR, CCPA, lack of consent. Processing and cleaning, risks of systemic bias introduced when filling gaps or removing outliers. Feature engineering and labeling, risks of proxy features that mask discrimination, data leakage, and poor quality labeling. Storage, security risks, breaches, and sovereignty issues when data reside in the wrong jurisdiction. Usage, risks of repurposing without consent, unauthorized secondary use. Destruction, risks of incomplete deletion and violation of the right to be forgotten. And now let's draw some conclusions. We've seen that data are not merely fodder for algorithms, they're a key asset that directly determines the reliability and safety of AI systems. We learned to distinguish structured, unstructured, and semi-structured data, understood the difference between labeled and unlabeled data, and why features and labels are the basis of all machine learning. We walked through the entire data lifecycle, from collection to destruction, and saw the technical, legal, and ethical risks at each stage. We also understood that data quality and transparency of provenance are not optional, they're necessary prerequisites for trust in artificial intelligence. And most importantly, responsible data governance is not a barrier but the foundation upon which trustworthy systems are built. Friends, here is our bonus quiz on the material from Lesson 2. 6 questions to test your knowledge of data types, features, labels, and the data lifecycle. Which of the following best matches the formal definition of data? Which data type is not considered structured? In machine learning, what is called a feature? Labeled data are those that. The immediate danger of data drift is that. At which stage of the data lifecycle do we create backups and delete obsolete data? Please pause the video and answer each of these 6 questions on your own. Write your answers in the comments below. We will review the most interesting cases together. If you found this lesson useful and don't want to miss the next ones, please like and subscribe. Correct answers and detailed explanations will appear in our Telegram channel, the link is in the description. See you there, and see you in the next lesson.